Hello everyone, I'm Ji Liu, a PhD student from NC State University. It's my pleasure to talk about my recent work, reliability modeling for NISQ-Era quantum computers. We start from the motivation of this work. Quantum computing has become a rapidly growing research field in the last few decades. Quantum computers have potential for solving problems in quantum simulation, machine learning, and work as quantum optimizers as they may provide high speedups over classical computers. The quantum computers with a number of qubits ranging from 50 to a few hundred are termed as noisy intermediate scale quantum computers. Although these quantum computers do not have enough qubits to accommodate the error correction circuit, they will be useful for exploring many-body quantum physics and provides benefit for a class of quantum applications. Due to the low fidelity of NISQ computers, it is important to measure and estimate the reliability of the quantum circuits. There are many types of errors in the NISQ systems, including decoherence error, depolarization error, crosstalk error, measurement error, and so on. On the right-hand side of the screen, we can find the output state distribution of the 3-qubit quantum phase estimation algorithm. The correct output state is 111, and in the figure we can find that the erroneous output state actually has the highest probability. And due to the complicated source of noise, it is difficult to estimate the reliability of quantum computers. The prior works have proposed analytical models and noise simulators for estimating reliability. In our work, we treat the quantum circuits as a black box and proposed a reliability estimation model based on the circuit characteristics such as number of qubits and circuit depth. We use a benchmark with random circuits to generate a large dataset for model training. We move on to the background of this work. There are different studies to characterize the noise in quantum computers. The first approach is quantum tomography. The quantum tomography gives a complete characterization of quantum states. However, the number of required measurements for quantum tomography increases exponentially. And randomized benchmarking is another method. It measures the average gate errors by running sequences of randomly selected Clifford gates and followed by a reverse gate that would return the qubits to the initial state. However, the Clifford gate set also increases exponentially. And in the IBM Q quantum computers, the reported gate errors are actually the average gate errors measured by randomized benchmarking. And due to the crosstalk error, these partial characterizations of 1 and 2 qubit error given by randomized benchmarking is not sufficient to predict the error rate of the system. And besides these quantum noise characterizations, we need a noise model to estimate the system level reliability. The first model is an analytical model named Estimated Success Probability Model. It is used extensively in noise adaptive quantum compilers. The variable g's in the equation are the gate error rates, and the m's are the measurement error rates. So the equation means the success probability of the system equals to the product of the success probability of all operations in the program. The limitation of this model is it does not consider the crosstalk errors. And the second model is the model from Qiskit noisy simulator. This model includes single and two qubit gate depolarization errors, single qubit thermal relaxation errors, single qubit readout errors, and all these error rates are based on a device property. The limitation is that it does not consider other errors such as crosstalk. And now we'll discuss what is the metric of reliability. The first metric is the probability of successful trail, also known as PST. PST is similar to the success rate in classical computing. It is the number of successful trails over the total number of trails. And the second metric is IST, which is the short form of inference strength. IST is the probability of the error-free output over the probability of the most frequent erroneous output. When IST is greater than 1, the error-free output has the highest probability and we can infer the correct answer. When IST is smaller than 1, the erroneous output will have the highest probability and we cannot infer the correct answer. And now we'll discuss how to generate the randomized quantum circuits. We treat the NISQ quantum computers as a black box and build a reliability estimation model based on the correlation between the characteristics of the quantum circuit and the reliability metric. We generate randomized quantum circuits to train our reliability estimation model. We collect the quantum circuit characteristics, PST and IST of each randomized quantum circuit. And we establish the reliability model with two methods, polynomial fitting and neural network. The IBM Q quantum computers support 5 types of basic gates. We assume that all the U1 gates have the same error rate despite the value of lambda, and so does all the U2 and U3 gates. Therefore, we can use the poly Z gate, Hadamard gate, and poly X gate to represent the U1, U2, and U3 gate. This hypothesis is in accordance with the analytical models and the noise models, where the gate error for all the U2 gates are the same. We first start with the benchmark with random number of single-qubit gates. In this model, we consider the following circuit parameters: number of single-qubit gates, number of qubits, circuit depths, and number of measurements. We also have a max gate variable to limit the maximum number of gates on each qubit. It is set to avoid the unnecessary data in our dataset. We fit the dataset with a polynomial model. Due to the limited size of our dataset, which is 1000, the maximum degree of polynomial is 4. As we increase the degree of the polynomial model, it becomes more and more accurate. Here in the table, the R is the regression value that measures the correlation between the observed outputs and the estimated outputs. And the MSE is the mean squared error, which measures the difference between the observed outputs and the estimated outputs. We also fit the dataset with a 2-layer feed-forward neural network with 10 neurons and trained with a Levenberg-Marquardt training algorithm. The training stops when generalization stops improving, as indicated by an increase in the mean squared error of the validation samples. The x-axis is the actual PST, and the y-axis in the figure is the predicted PST. Ideally, the predicted value should be the same as the actual one. Therefore, all the data points should fall on the line of equality. And the closer to the line of equality, the more accurate estimation is. We compare the estimated PST and the observed PST of the Bernstein-Vazirani algorithm with different qubits. This table shows the R and MSE of different models. As we can find in the table, all the models fit for this Bernstein-Vazirani algorithm. Then we generate random quantum circuits with 2-qubit gates. The random 2-qubit gate benchmark includes randomly distributed CNOT gates. We found that counting the number of CNOT gates is not sufficient for an accurate model, and we need to include the topology of the circuit. A directed acyclic graph can be used to describe the circuit topology. However, when the circuit is complex, including a DAC will include too many parameters. To overcome this problem, we propose a method to extract the features of the DAX-based circuit description. Since the connectivity map of the backend is known, each CNOT gate must be mapped to one connection between qubits. So we can count the total number of CNOTs for each connection. For example, the 20-qubit machine, IBM Boblingen, has 23 connections. Therefore, we can use a vector that consists of 23 variables to describe the circuit. And due to the large number of parameters, the polynomial model is limited to 2 degrees and it does not fit for this benchmark. And the neural network model, the Qiskit noise model, and the ESP model fits for the randomized 2-qubit gate benchmark. And finally, we experiment with the random circuits with single and 2-qubit gates. The accuracy can be improved by including more parameters for single-qubit gates. So we define a single-qubit gate count for each qubit. The epsilon ID, epsilon U2, and epsilon U3 are proportional to the error rates of ID, U2, and U3 gate, and the epsilon U3 is normalized to 1. To evaluate different models, we examine the absolute difference between the estimated PST and the observed PST. The smaller, the better. And as we can find in the figure, for most of the benchmarks, the neural network model has the most accurate estimation. And we report the parameters we considered in this neural network model. We also report the R and MSE of different models. The neural network model has the highest regression value, which means it has the best correlation, and the smallest MSE, which means its estimation is closest to the actual result. And the inference strength metric determines whether a system can infer the correct answer. This table shows the observed IST and the estimated IST of different models. The ESP model is only used for estimating PST, and it cannot be used to predict IST. So we compare our neural network model with the Qiskit model. For the purpose of predicting whether the system can infer the correct answer, we can set a threshold k. And if the estimated IST is greater than k, the system is likely to infer the correct answer. And we set the parameter k equals to 2 in our experiment. Our model can correctly predict that the system can't infer the correct answer from the 4-qubit and the 6-qubit QFT circuit. We run the prior experiments on a 20-qubit machine, and the Qiskit simulator only supports maximum 32-qubit simulation. To test the scalability of our model, we run the 35-qubit Bernstein-Vazirani algorithm on a 53-qubit quantum computer. The observed PST is 0.9%, and the estimated PST of the ESP model and our neural network model are 0.5% and 0.7% respectively. And the observed IST is 1.57, and while the estimated IST of our neural network model is 2.23. And we compare different models from 3 aspects: accuracy, execution overhead, and scalability. In terms of accuracy, the prior results show that our neural network model has the highest accuracy. And when predicting the PST of 20-qubit Bernstein-Vazirani algorithm, the execution time of the ESP model, our model, and the Qiskit model are 1.6 millisecond, 7.7 millisecond, and 8 minutes respectively. And considering the scalability, both the ESP model and our model are scalable to model the 53-qubit machine. We'll move on to the use cases of our model. First, our model can be used to evaluate circuit designs. Here we have two different designs of the quantum phase estimation gate. Our model can be used to choose the best design before running them on the real quantum computer. As shown in the table, our model successfully estimates the modified QP gate has higher PST. So we will choose the better design before running it on the real quantum computer. And our model can also be used to improve the qubit mapping. In the Qiskit compiler, choosing different initial edge will lead to different circuit mappings. And our reliability model can be used to compare these quantum mappings, these circuit mappings at compile time. The compiler can return the top 8 mappings and expect the best mapping is included. And the existing works that rely on a noise model can also take advantage of our model. For example, in the Ensemble of Diverse Mapping study, based on the ESP model, the researchers find top 4 best mappings and merge the outputs to get an ensemble of diverse mappings. The ensemble will have better IST. And as a result of a more accurate model, the ensemble generated from our model has the highest IST. So in conclusion, we propose a reliability estimation model based on the characteristics of quantum circuits and the connectivity of the target quantum computer. We show that our reliability model outperforms the noise model from Qiskit and the ESP model from previous work. Our model can be used for guiding the quantum circuit design. As a result of the low execution overhead, our model can aid the compiler to select the mappings with higher accuracy at compile time. That's all. Thank you for listening.